Hello everyone, my name is Cedric Amlot and today I'm happy to discuss our research with you, which is titled Evaluation and Optimization of Ballistic Counter S-UAS Solutions. So over the past decade, the proliferation of small, cheap and easily modifiable commercial drones has fundamentally changed the modern battlefield. They are used for intelligence, surveillance, reconnaissance, and increasingly as direct attack ammunitions. As the threat has evolved, so must our countermeasures evolve as well. So today I'm going to walk you through an original framework and software tool we've developed to assess how effectively traditional and modernized ballistic weapon systems can neutralize these threats. So let's start by looking at the broader counter SUS landscape. When we talk about neutralizing a drone, we generally categorize effectors into four main families. First, we have the kinetic effectors, which we can divide into guided and unguided effectors. Then we have wireless link related technologies as jammers, spoofers, hacking systems that target the drone's communication or navigation. Third, we have the entanglement systems, which are basically nets. And finally, we have directed energy, such as high energy lasers or high power microwaves. And when we look at the kinetic family, for the scope of this research, we are focusing on the unguided kinetic effectors. So these can be unitary rounds, mostly small caliber rounds, as a standard rifle bullet, for example, and fragmenting rounds. When we look at the unguided kinetic effector, we essentially are looking at the weapons that form the backbone of most ground forces. So there's three actors in our scenario, and those are just the projectile, its launcher, and the target it is trying to impact. And for the unguided kinetic effectors, we will be evaluating small caliber projectiles. Think of a 5.56 NATO round. And on the other hand, we have the medium caliber fragmenting projectile. And there's many variations of both, which we can evaluate with our tool, launched from a whole set of different launcher systems, of weapon systems. And today I will walk you through our methodology that we developed, which is the core of this presentation essentially. And then we will look at the results and discussion as we've applied it to an experimental data set, and we will then wrap up with conclusions and perspectives. So for the small caliber rounds, we're evaluating what happens with the target when we fire unitary projectiles, so one or more towards the target. On the other hand, for the medium caliber fragmenting projectiles, we're not going to aim directly to impact the target, but we're going to fire around the target in order to create a cloud of fragments. But for both systems, we're going to build the methodology such that it will provide us with an answer to the question if they're able to neutralize the SUS, or we're at least going to try to quantify that. So let's dive into the methodology now. Evaluating a kinetic counter SUS engagement system, is an interdisciplinary task. We had to model 6 domains, basically. So the targets we've been looking at the projectile trajectory, fragmentation, interception, uncertainty, and survivability. We've programmed that into a Python framework, and if you would map out how all domains are related, this is the diagram to use. I would propose to start with the target, and here there's mainly 3 domains that we have modeled. We'll start with its trajectory. So for the 2 main types of targets, so rotary wing and fixed wing drones. There's two, we can, all the scenarios they fly, we can divide them up or we can abstract them into two types of scenarios. Basically, on the first hand, the ISR scenarios, so those are the intelligence, surveillance, and reconnaissance scenarios, which are basically observation scenarios, and on the other hand, the direct attack scenarios. And due to their fundamental differences in how they generate lift and how they fly, the rotary wing and the fixed wing drone will execute slightly different scenarios for each type. And in our tool, we've modeled it as a combination of linear segments. Now onto the shape of the target. For our fixed wing and rotary wing target drones, well, we're going to model them as a combination of ellipsoids. Why? Well, if we look at the medium caliber fragmenting rounds, the idea is that we have to evaluate thousands of interactions of the fragments with the target, so we need swift, simple mathematical computations to occur, as we cannot expect for the computations to take long. In an operational environment, we would need a swift response from the system. Then onto the response of the target, what happens when the projectile arrives at the target. Well, there we primarily looked at the primary component, so to speak, that a projectile would encounter, which is the shell. And of most commercial drones, the shell is made out of a certain type of plastic. Now, if you look at the shape, you notice that has been optimized for material use. At the backside of this shell, you would see several structural reinforcements, for example. So in an academic research environment and an academic testing environment, that target would not be the most optimal one. Because if I hit the target on this piece, that will lead to another response as I would hit the target on that piece, for example. So we found an equivalent plate, we call it an equivalent plate, which is just a plate of that same material, and we characterized the interaction of the projectiles with both target types. And that interaction is characterized by a ballistic reference metric named the V50. So that's the velocity at which 50% of the impacting rounds would perforate the target. And as you notice, the V50 of the equivalent plate is slightly higher than of the shell. So we say that the equivalent plate is a conservative representative of the shell. Onto the projectile trajectory, we'll be looking at the main ammunition and what do I mean by that? Well, if you look at the engagement with both principles, in the case of the small caliber rounds, you just have a ballistic flight, a ballistic phase where you're firing towards the target. However, for the medium caliber rounds, there's an additional phase to consider, namely when the projectile arrived in its detonation position, so to speak, there's still the phase of fragmentation to consider. And so the methodology has been prepared such that any trajectory model can be implemented, both for the ballistic flight and fragmentation, but the fragmentation model will oftentimes be a simpler model than the ballistic flight. If we dive a bit deeper into the fragmentation itself, well, if we consider a 40mm grenade, for example, that contains pre-fragmented projectiles or fragments, then this is a typical use case where this weapon system is manually operated by an operator. And so, as the name says, it consists of pre-fragmented projectiles. So the primary fragmentation really comes from those pre-fragmented projectiles. And so if we cut a projectile open or an ammunition open and we zoom in on this bit here, we notice that there's a composition of rectangular and spherical fragments. And so we'll model this ammunition into dedicated software, and that software essentially gives us a fragmentation pattern with flight directions and velocities. We will use that 2D fragmentation pattern into our methodology to recreate a 3D fragmentation pattern and to look at the interaction with our target models. Now that we have an idea of the trajectory of the target and of the projectile, we can combine them to look at what happens during interception or the interaction between both. And the idea here is to compute a solution to provide the weapon system to fire towards the future point of the flying target. So the target is flying from the right in this case, and the solution will aim within a specific tolerance with respect to the center of the drone in this case. Now, all the grayed out boxes are purely theoretical concepts, but ballistics is filled with uncertainties, so to ensure our methodology comes closer to reality, so to speak, we need to characterize or quantify uncertainty. And the way we do that is by quantifying uncertainty on the input parameters, so that's muzzle velocities, elevation angles, ballistic dispersions, and we run samples, we run simulations on our methodology. Now, the results of those simulations will allow us to statistically quantify the interception point. So we will have a mean or an average interception point and standard uncertainties of that interception point. Now, with that quantification of uncertainty, that allows us to pass on, we all have all the tools now, all the quantities in hand to characterize survivability. Now, survivability of the target when a projectile impacts the target, or its complement, which I would say neutralizability, which is the ability of the projectile to neutralize or to kill a target, is quantified by a kill probability. And in its most fundamental form, it depends, or it is composed of two other probabilities, namely the hit probability, which quantifies the hitability, so to speak, and it can essentially be computed by running a enormous amount of simulations and then just counting the number of effective hits, which would give you statistical distributions of the impact position. On the other hand, we need to look at lethality, which is quantified with a kill if hit probability, and it is a very complex task to do, so much so that it is often quantified with expert estimates. And the way you should read these values, for example, for the nose here, is that there's a 90% probability to kill the target, so the target as a whole, when a nose is hit with a velocity above the characterized V50 value. So this slide shows you that all the boxes are now grayed out, so which means we have all the tools in hand to apply our methodology. So let's dive into the experimental case. 5 operators were tasked with neutralizing an inbound target, several inbound targets, and the flight patterns those targets ran are these ones. So those four different flight patterns that are combinations of linear segments, or at least represented as linear segments in our methodology. And for the sake of the results, let's focus on the ISR mission, so the observation mission executed by the rotary wing drone. So when we use the methodology, when we apply the methodology, this is a typical result it could provide us. We're looking at a range versus deflection graph here, where here those 5 points, black points, are the 5 operators, and you notice that the flight path, the flight trajectory of the target is here color coded, so it flies from the red dots, which are waypoints, and it has been color coded with the kill probability. And intuitively speaking, this makes sense. It just says that the closer the target comes to the 5 operators, well, the higher the kill probability will be. Now, the utility of the tool comes when we can generate a lot of simulations for a varying number of shots, for example. So in this case, we're looking at the kill probability for a target positioned at a distance of 300 meters. And we're going in the simulation, the numerical simulation, we're going to vary the number of shots. Now the orange dot is our experimental result here, so that's approximately a combined 170 shots. And what you notice is that on average the numerical results and experimental results align quite well. Now, to conclude these results and the methodology that we've explained, well, we've built an original software tool that allows us to assess the use of unguided kinetic effectors as countermeasures against the threat posed by drones. We can virtually run any number of scenarios given the modularity. It's just a scenario can be implemented as required. We have generated results for small and medium caliber rounds, and the tool gives us insights into the specific use of unguided kinetic effectors. So what are the engagement distances to consider, which calibers would we have to prefer, and for example, is the additional shot worth the cost, for example? Will an additional shot lead to a significant improvement in the kill probability? The model aligns with the test data on average, but more testing is definitely needed to strengthen the validation process. Thank you very much for your attention, and I'm happy to answer any question you might have.